Welcome to the SEI podcast series, a production of Carnegie Mellon University's Software Engineering Institute. The SEI is a federally funded research development center sponsored by the U.S. Department of Defense and operated by Carnegie Mellon University. A copy of today's podcast can be found at the SEI website at www.sei.cmu.edu/podcast. My name is Suzanne Miller. I'm a principal researcher here at the SEI. And today I'm very happy to welcome once again to our stage Peter Feiler, one of my friends and colleagues from long way back, who's here to tell us about some of the latest work that he and his colleagues are doing with AADL and some of the derivative kinds of research that's come out of that. So Peter, welcome. Thank you very much for joining us today. I know you have travel plans in the near term that will probably be taking you away from us for a while. So thank you very much for making the time.
Sure. Thanks for the introduction, and welcome to you too.
So tell us a little bit, for people that don't know about AADL, just give us a little sort of 30 seconds about what is AADL and what's important about it. And then what are some of the challenges that you have dealt with in your work with AADL?
Yeah, the focus of AADL is on safety-critical software systems, like ones they find in cars and so on, and we see plenty of evidence of issues with those.
And you know, I just realized I just said AADL, and we haven't told our readers what AADL stands for, so why don't you go ahead?
We'll get to that in a moment, yeah. So the problem space we're dealing with is embedded software systems, especially safety-critical. What we are encountering is that things go wrong, and we don't detect that until these systems are in operation. So there was research in the 90s, and we then turned that into an industry standard on modeling architectures and doing it through a language that has strong semantics so you can analytically assess how the system will work. And we used the term virtual system integration as a concept to drive that idea forward. So the standard has been originally published in 2004. We have done work on it. Industry groups have embraced it, like the aerospace industry and and others as well. And we also have been extending the standard suite. There's a number of annexes to the standard, and we also have been publishing revisions of the standard. So the standard activity is quite alive, and its application is quite alive as well.
So what are some of the challenges once you have a language like this? I'm sure that as soon as you have one thing, now you need another. And so what are some of the things recently that have led to this most recent work?
Yeah, so when you deal with an embedded system, the initial focus with AADL is to characterize your system, both the software, the hardware, and the physical system it's dealing with, in such a way that you can focus on understanding the interactions between the parts. Because that's where 80% of the problems that we discovered today don't occur until post-unit test, and it clearly indicates it's those kinds of things. So that has been the focus. 5 years ago, we were asked to do a study to help see how we can improve qualification of systems, and that's when we realized to say, doing the development is fine and improving it, but when we are doing the qualification, we do it against requirements. So we need to improve the way we specify requirements, and we want to keep a record of all the evidence we are collecting, not just in the final test, but throughout the whole development process. And so that led to a project that deals with incremental assurance, a project called ALISA, and it's in that context where we developed this language called RecSpec, or Requirement Specification Language, which is today's topic.
Okay. Yes, and so in traditional developments, requirements, specifications, still, I mean, we're modeling all kinds of things, but we still tend to write those in English or native language, in prose, using, typical is the system shall do this, that, or the other thing. And what kind of information is lost when you use that kind of requirements basis instead of doing something that's more model-based and that has some stronger semantics?
Again, studies have been done on that front, and what you find is that a lot of the issues are introduced during the requirements phase, and it's often because they're missing requirements, there's ambiguous requirements, there's just...
There's a lot of assumptions. I know when I wrote requirements, I'm creating a mental model of what I want, and I have English prose as my way of expressing that. It's very difficult to express essentially what we would put into a model when we're using that kind of a prose expression.
Yeah, exactly. And so there's a couple of ways forward, and people have tried to the one way that there has been quite a bit of research is to process textual notation and try to extract from it, for example, on the behavioral part, a state machine. And then once you have a state machine, you can figure out,
Sure.
are you missing some state, are you missing some transitions
Right.
and things like that. But that's just one piece of the puzzle. What we have said is then complement that research and leverage, obviously, but to say, can we come up with a technique that helps us make sure we have coverage?
Okay.
Because like I said, 80% of the problems are not necessarily on the formal part, but simply you missing certain things.
Right.
And so this is where we then have an approach, we call it architecture-led requirement specification, and I'll be elaborating on that when we get to the use scenarios.
Okay, so the SEI, I'm just laughing a little bit because we have many things now that are architecture-led, architecture influence, and many of us at the SEI strongly believe that architecture is kind of a key communication vehicle, and it's just like every time we do something else, we run back into that is actually one of the core elements that we have to deal with. So tell us a little bit about the requirement specification, RecSpec notation. How is it different from textual processors for state machines and other things that people have tried?
Yeah, we got into this notation by building, again, I like to build on other people's work so I don't have to reinvent the wheel.
Makes sense.
It turned out there was a research group in France who had been looking over that requirement specification space, because again, there was research in the late 90s and early 2000s on that front. And so they were building on that and looked also at what people do in SysML and so on, and came up with a proposal for a meta model for requirement specification associated with AADL models, and brought that to the committee.
Okay.
In that meta model, what they wanted to do is focus on the ability to specify stakeholder requirements, or sometimes also called goals. This is where this goal-oriented requirements engineering came from. And system requirements. The main difference is, and you want to have an explicit separation of those two. Stakeholder requirements, they sometimes can be in conflict with each other, and you can't necessarily resolve them and those kinds of things. So you need to give space to express everything, and you want to make sure that everybody talks about all the requirements and assumptions.
Right.
Then you turn them into system requirements, and system requirements need to be verifiable, because otherwise you can't qualify against them.
Okay.
And so in our notation, we support both of them. And for both of them, we do it by associating them with a specification of your system. In some cases, you use the architecture language not to describe the internal architecture of the system, but the system in its operational context, because that's a system as well.
All right. So you're including the environment then as part of what you're describing in the requirements envelope, I'll call it.
Exactly. And so when you do that, I've seen plenty of these documents where on the stakeholder side, they first describe a use scenario that says, for example, for a situational awareness system, I need to track electric power lines, I need to track other flying objects, I need to track mountains and this and that and the other thing. And then at a later stage, when they elaborate those requirements, they forget half of them.
Yes.
I mean, it's simple things like that. If I now have
a
model where I say, here's my system and here are all the entities in my environment, I now have something specific to point to and make sure I have covered each of those and have covered them from a variety of angles.
Okay. So you are basically doing a model of the environment and in which the requirements are meant to satisfy goals, as well as modeling the goals, and then as well as modeling the expression of how you think when you start, the system is going to be able to actually achieve those goals.
Exactly, yeah.
Okay.
Yeah, so there's a number of scenarios that we can make use of. If you already have a stakeholder document that was collected separately and it's a paper document, we can import that into our representation, and then you use that as a basis to start focusing on how to define the system requirements, and you do those around now your architecture specification.
Okay.
If you don't have stakeholder requirements yet, you may already at that point want to define those in the context of an architecture representation. So basically we have two formats for the requirements. One is kind of one that follows a document structure, sections and so on.
Yes.
And then another one that follows the architectural elements.
Okay.
And you can interlink those so there's full traceability and all the way back to individual stakeholders.
And that also enables a different kind of discussion about what, and you can get into, so I do a lot of work in Agile, and the Agile sort of requirements way of dealing with things often is called a story, where you add into the what a who and a why.
Exactly.
And so this is a different way of getting at that who and the why. You're dealing with the stakeholders explicitly. The why is coming from the context. If I can't figure out the why directly, then I'm probably going to ask about it. And so now we can have a discussion about what really drives this, find a new element that we didn't know about in the architecture, and all those kinds of things.
Then
Excellent.
And then the second part of it is you have the requirement for the system as a whole. Is you evolve your architectural design.
Yes.
Are those requirements moving along to the various subsystems or not? Most of the time, they tend not to.
Something happens, yeah.
By using our notation, it's a very natural, it's the same mechanism that lets you say, okay, when I do my next level design, I now define the assumptions that I make about the parts I'm using. Guess what those assumptions are? They are effectively the requirements I'm placing on the thing that is to be developed, or that you're going to buy and put in.
Right, right.
And so that's how then this whole process becomes an incremental process of pushing requirements down. And at the same time, as soon as you have done the next level of design, based on those specs of the next level, I can already verify whether the upper level requirements are satisfied
actually covered,
at this level.
Yeah.
And so you get this continuous incremental assurance
So
activity.
this has been part of your real focus, is getting things in place that allow not just virtual system integration, but the incremental assurance,
Exactly.
which is a very expensive part of certainly DoD systems and other complex systems. So this is a way of enabling going up a little bit higher sort of in that space.
Exactly.
By having something that's verifiable all the way up to the stakeholder requirements.
Yep, exactly.
Nice. Very nice.
Well, it's fun work to do.
Okay.
And as we have been developing that, we had the opportunity of actually applying it with an external customer. There is a Army technology demonstrator program called Joint Multi-Role.
Okay.
They had a project where they were leading some work with 2 contractors and some internal integration team. We then came in late into the like partway into the project.
Okay.
We then did a shadow project, took the requirements that was given to those contractors, captured those in this notation.
Nice. Oh, wow.
And then in that context, again, early on, tried to see if we can identify some holes and some potential integration issues. And that was then validated, and we identified about 85 issues in the requirement specification. And that was confirmed by the contractors, yes, those are then issues that we
have to resolve
and that kind of thing. And as a result of that, now in the next round, and they just had a BAA out and are currently leading the contracts, and they will lead 6 contracts where they didn't require the contractors to use it, but they strongly encourage contractors to use this whole concept of virtual system integration.
Right.
And in that context, we are offering, as part of the tool set that comes with AADL, the OSATE tool set, the rec spec support is already included.
It's now. I was going to ask you about that.
It's already publicly available for people to use,
Okay, so if I'm a software architect, or if I'm a requirements business analyst, and I have already been using the tool set in OSATE, I've already been using AADL, I can extend easily into this.
Exactly, and it already comes with the standard release now.
Okay. What other kinds of support do you have for people that want to learn about this and want to become proficient at using RecSpec?
Yeah, one of the things that we have is a tech report that just came out that elaborates on all the elements of the language, because there's a rich set of capabilities underneath it. So to just give you yet another example of how we try to home in on semantics of these things and sometimes distinguish things. The guys that came with the meta model distinguish between verifiable requirements and satisfiable requirements.
Okay, and how do they distinguish those? That's an interesting set of words.
They used those words, and I think one of them was traced back to the SysML crowd.
Okay.
But verifiable means yes or no. There's no question.
Okay, it's a binary.
It's a binary decision.
Right.
Satisfiable is, I would like you to build a car for me that goes 250 miles an hour. it's kind of a design goal.
I'm sure you would, Peter, but don't get over it. Maybe 120.
And then given you have
Yeah.
conflicting requirements,
Gotcha.
and given I can do, there is some room for negotiation. So it's
Okay.
a kind of a goal that you set, and then what you do is, as part of the process of taking stakeholder requirements and turn them into system requirements, you then kind of make a trade-off.
So it's a trade space kind of requirement.
Exactly. So what we have now is actually support in that notation to not only specify requirements that are musts, but also design goals, saying, this is what I want as a minimum, but this is what I would like to have, and so that then allows us to...
We sometimes call those thresholds and objectives.
Exactly. So
in DoD
people
language.
use similar terms. So it's stuff like that that we have in the notation. The other piece that's around it is part of the methodology of doing this thing is to say, how can we, first of all, there's all this traceability stuff all the way back to stakeholders and up the, as you go, the architecture up, and from the system requirements back to the
implementation.
To the stakeholder requirements and forward into the implementation. But we also have some support in there that allows you to analyze the specification for coverage. So in coverage, we do it along 3 dimensions. One is along the different elements of your system model. Like when you said when you do stakeholder requirements and you say, I have a system that deals with 15 different types of elements in my operational environment. I now need to make sure there are requirements and assumptions you're making about each of those.
Sure.
Okay.
Right. Yeah, because they're all going to have different effects on the system.
Exactly. So this is it's, if that's 80% of the problems.
Yeah.
We do that. The second piece is to then say, can we make sure that you're talking about all different interesting or quality attributes, especially operational ones that are important to you?
And these are the non-functional requirements that pervade the system.
Non-functional properties or non-functional requirements. Or SEI terminology. I specifically then call them operational ones because those are the ones that deal with the operation of the system, like safety and reliability versus is this thing maintainable or is it modular?
Right, gotcha.
And for that, we are just incorporating elements that come from other work at the SEI, namely from ATEM, for example, the utility trees, because they give us a very nice framework for saying, have you talked about security, and under security, have you made the requirement concrete enough that it's measurable?
Right.
Because we need to verify type of thing. And then the third part of it is, and this is where the safety criticality comes in, is we make use of the error model annex of AADL, and I think we have a blog on that before. Or if not, we'll be doing one shortly. As part of that, we have a taxonomy of fault propagation types.
Typical fault propagation.
And typically what people think of is the thing works or doesn't, but there is many more variations on that theme. So we, again, can then use that taxonomy to make sure and point out to you, hey, you have a data stream there. Have you talked about data rate problems? Have you talked about value problems? Have you talked about time-sensitive data problems? Those kinds of things we can address as well.
And that is a domain-specific model. That's an aeronautical systems model.
Yeah.
In the future, there could also be medical device models. There could be other domain-specific models.
Actually, the taxonomy is for the kind of fault that gets. It's kind of the kind of impact that it can have on a fault, and that is a very generic set. It's a limited generic set. There's a second class that is then domain-specific. Because if I provide you with a subsystem, a black box subsystem, you don't really care of how it fails internally. If I'm a GPS and I'm supposed to provide to you with location data, what you care about is, do I provide it to you or not?
Yes.
Do I provide it to you too late or too early?
Yes.
How accurate is it? Do I send bad data? Do I send it at the right rate?
Yeah.
It's that kind of thing that you care about, and how it internally occurs, that's obviously a domain-specific problem, but the taxonomy focuses on the impact because that's the interaction part that we typically struggle with. People know their domain. I'm leaving them to do their thing, but what we do is now look at the architectural impact of things going wrong.
And things going wrong in operations.
In operation. And so what you have is you have exceptional conditions. You want to make sure that they're handled, and we document which ones do you assume don't occur and which ones do you assume do occur that you're willing to handle. And I use the word exceptional condition or fault conditions because what we then do is our current focus has been on the safety implications, but with more recent research work we said, the same exceptional conditions have also security implications. So that framework is extensible not just into the safety, but applicable to the security.
And that's one
arena as well.
reason we call it incremental assurance, because assurance is not just security or just safety. It has multiple dimensions. And many of them share attributes that you can take advantage of in these modeling kinds of activities.
The other part of it is we already said that requirements need to be verifiable.
Yes.
The way we do that is then, as part of the specification, you then, that's not part of the RegSpec language, but a set of other notations that are being done under this ALISA project.
Right.
And we will be talking about that at a later stage, is you have a verification plan where you identify what are different verification activities that need to be done. And with verification activities, it's not just manual things like look over this document, but us running analyses on these actual
particular
models.
Analyses.
Yeah, and given we have that specification in place under this ALISA project, we will have then automated the execution of these things as well, and the automatic generation of assurance cases as kind of an evidence type of thing as well. And like I said, it's beyond the topic of today, but
but this all connects.
One of the reasons we want to improve the quality of the requirements is because that's the thing that we verify against. And so there's a clear link by saying, if I define a requirement, I also want to define how I'm going to verify it. It helps you make the requirement sharper.
And it also, I mean, I think a key thing here is you're finding a way to get to missing requirements. And so if I verify against the requirements are there, but I'm not verifying against requirements that I don't know about, I'm missing.
Exactly.
Those are potential fault areas that are gaps that are very important. So this is a way of minimizing some of those gaps.
Yeah. So I referred to the tech report, but there is also a report about the work that we have done with that Army group that I mentioned, and it illustrates how that particular example. And there's actually a total of 3 reports that are specific to that work. They are SEI reports, SEI special reports that are available as well as the report that documents the language itself.
Well, I'm sure that many of our listeners will be very interested in those, and I am interested in them. Someone that used to write requirements, and I want to see what the latest is on requirement specification, because I have to believe, I mean, back to the 80s when I was doing this, regularly, it was so painful. And always so much pressure, because you knew that that you couldn't make it perfect.
Exactly.
And we've been acting in many ways as though we could make it perfect, but we know we can't do that with prose. So we may not get perfect with RegSpec, but we're going to get a lot closer with that, I think, than we can with prose.
Exactly. So it's a language. It's a textual language, so you can process it nicely and everything. There's a meta model behind it, and so what's going to happen now is we are taking now the textual language back to the AADL committee. Because standardizing around a meta model isn't sufficient. We needed something more, and so take it back to the committee so that this language now will become one of the annex standards, like the error model as well. This is one of the things that one of my next steps, just specific to the RegSpec.
So RegSpec is well on its way. What else is coming? You've got the incremental assurance work. What's next in that sort of whole range of things that are related to incremental assurance?
Like I was mentioning, we have a language that lets you annotate verification plans. The whole thing is compositional, so you can do it for large-scale systems. We have an implementation of the whole thing. In terms of verification activities, we support a wide range of things that can be used to specify the analysis. We have incorporated technologies from other groups, like Rockwell Collins, for example. We are doing that under a 2-year line project, which will close out in September. So in August, we will actually have a public release of these verification capabilities as well. Other work that we have is we have an ongoing project where we took this work into the security arena. And there what we focus on is to say, given we have a specification of security policies, namely, for example, that certain information is only accessible to certain people, or if you're in an embedded system and you're supposed to be able to switch on and off the light bulb, you are not supposed to reprogram the router built into a light bulb and Internet of Things type
not.
of things.
Yeah.
Well,
yeah.
today there is no clear
Yeah.
specification and no enforcement. So what we are doing in that project is to say, first, if you have such a specification, if you then look at the implementation, are those policies actually enforced?
Okay.
Type of thing. And so we are in the first
And you can
year.
do this now in a virtual way by having
Exactly.
a good model of the system.
It's again a 2-year project. We're at the end of the first year. We have already some interesting results. What we have come up with is attack surface identification and attack tree generation and analysis, and also generation of implementations against a verified kernel so that you can produce implementations that are fully secure. And we are in the middle of releasing those tools, actually probably at the end of this month as some work. And then the final thing is something that we are heading towards is, and I just I'm working on a proposal for that, is to support trade space exploration. When you design your architecture,
Sure.
you have a bunch of options. How do you figure out what are good candidates? If you have a large system, there's so many different places where you can make choices.
Yes.
There has been some interesting research at the system engineering level where people have used some techniques, some of them combination of statistical and others, for things like satellite architectures to explore new ones, or for aircraft and so on. And so we are taking those concepts and now applying them for the embedded software system as well, is the proposal that we just are putting out. So it's again a nice extension.
Yeah.
We just try to build on what we have and expand out into additional areas.
One of the interesting things that comes to mind to me when we talk about that is there are different points in the evolution of your architecture where you know different things. And so you can't do a whole trade space analysis at the beginning because you're not going to know enough to be able to make decisions. But if I've got incremental model building, incremental requirements, I can do incremental trade space analysis as I'm imagining at some point you'll be able to flag, hey, we have this data now, so this kind of trade analysis that we couldn't do 6 months ago, we can do now.
Yeah.
That's very exciting.
Yeah, and it's kind of interesting too because you find different classes of trades that people are interested in. In some cases, they just want to tweak the rate at which they're processing things. In other cases, they want to add some functionality or not, or pick one vendor over the other. But then there are some choices that have major architectural implications where we bring a new concept in. Like, should I go partitioned or federated? Should I use a pull protocol or a push protocol? Or one is when I produce data, it's immediately shipped, or do I request the data before it's being shipped, type of thing. And we have analytical techniques that let you find out what the implications of those choices are.
And another light bulb just went off for me when a lot of the slowness in adoption of parallel processing has to do with some of those architectural choices and not necessarily knowing, not being able to know until you implement what the effect is on total performance. When we have the ability to model several processors in parallel, we can make some of those analyses much more effectively.
Yeah, and so that, to come a little bit to a closing too, but also why I'm still excited to work at the AADL committee. And by the way, my next trip is actually to the committee in Germany next week. We actually have a strong group of researchers that come to these meetings because they have seen this as a very interesting platform to drive their research, and by doing that, immediately have a reach into companies that are trying to use these technologies.
It's a very short transition space.
Exactly, and so that's where you have groups that get at some of these issues. So for example, right now there's a group of folks led by Jean-Pierre Talpin from India that are taking the concept of synchronous systems and expanding it to stay within the formal framework that they have, but still allow more flexibility to deal with more concurrency, more asynchronous system behavior and things like that. And so that's kind of what makes it exciting, is you have one foot with the industry and the other foot strongly embedded with the research community.
Excellent.
Yeah.
Well, as always, Peter, I love catching up with you and finding out what's in your head and what's actually made it out of your head into the world. And we started this journey
long time ago.
I don't want to say how long ago, talking about model-based engineering and the role of a language like AADL, and the fruits of that are absolutely wonderful at this point. And I see just more and more coming coming into the real part of the world. So that's very exciting. All right, so let me tell people about where things are for them to find, because you have things all over the place. AADL itself, if our listeners go to aadl.info, you will find a wealth of resources and links to other resources. SAI also maintains a GitHub repository with downloads of different elements of the language and other information. And of course, with this transcript, we will provide a list of resources, because there are several that Peter mentioned, and we want to make sure that everybody has access to those. This is a very rich discussion. Thank you very much, Peter, for joining us.
You're welcome.
I do want to highlight the fact that, as always, you can contact us through info@sei.cmu.edu. And that's another way that you can get information that we may have missed in our resource list. And as always, this podcast is available on the SEI website at www.sei.cmu.edu/podcasts. And it will be available on the Carnegie Mellon University iTunes U site. Thank you very much for joining us today.